So, in light of me not be able to record 7.8 in time, and also in light that it was probably a good idea, just considering we already have kind of understood and mastered a bit. I'll be covering 7.6 here, like in detail. It's not really that difficult of a concept or like a difficult of a section. Essentially, the idea is going to be that you're given an integral and you might have to make a use of in it, but once you do that and get into a form, there's a table of integrals in the back of the book that you just refer to and you say, oh, well, that's the integral I need, and then you just go back. Okay, so you can feel free to read that section. It's pretty intuitive. To reflect kind of the change, I originally had a set of problems that I was going to have you do on the homework, which is still on the homework, but it is on the bottom now, and it is labeled EX, just like extra. So those are, I'll have those worth a little bit of just extra credit if you decide to do them. Again, they shouldn't take too long. You just got to make like the one use of, basically. I think in maybe not all of them, but some of them, we put the answer out. But I'll be skipping that for now. So we're going to move on to section 7.8 today, which is going to be improper integrals. Just finishing off chapter 7 as we move on further. Okay, so 7.8. What does it mean to be an improper integral? Okay, well, I'll demonstrate by an example. What's weird about this integral?
The upper limit is infinity.
Yeah, the upper limit's infinity, right? I mean, we're not just going to some number, but we're going to infinity. Now, as you might guess, I mean, that shouldn't be a typical case, because oftentimes if I just let my function go towards infinity, then I'm not really going to be able to get a whole lot from it, right? So like if I, instead of 1 over x squared, let's say I put x squared in this, well, that would be weird, right? That wouldn't really make a lot of sense, because if we think about the graph of x squared, right? If we start at 1 and then it says to infinity, so that means that we go all the way this direction, right? It just keeps blowing up and it keeps getting bigger. Like that's not going to give you anything. Like you're not enclosing anything. Like it doesn't work. We don't like that. So why do we even bother talking about it? Well, we do have some integrals that will give us an answer. And so, and in some cases, these integrals are actually really valuable for us to know, because they will tell us something interesting. We actually have, I think at least in statistics, there's a few kind of curves that are dependent on knowing the area underneath the curve from negative infinity to infinity, right? To be able to get the size right and be able to determine everything. So it is worth being able to know how to work with these types of integrals, right? But again, the thought is just weird to us, because I'm not simply just taking, one point to another, but I'm taking 1 point towards infinity all the way to the end, right? So the question is, what do I do with an integral like this, where it is kind of improper, where I can't really just plug in infinity? I mean, yeah, I might approach 0, but that's not really a value in here. Well, here's what we can do, right? Let's suppose that instead of going all the way towards infinity, that I stop at some point, okay? I'll call it t, right? And so we're going to say, maybe for this integral, for example, going to do the integral from 1 to t of 1 over x squared. Okay, that t can be really anything past 1, but it doesn't matter. Okay, now is this one that we know how to do? Like, is this an integral we're familiar with? Right? T is just some arbitrary value, right? Some number. We can do this, right? What is the integral of this one going to be? Yeah, thank you. So we get negative 1 over x, and we're going to go from 1 to t, right? And then I just plug both these numbers in. So I get negative 1 over t minus negative 1 over 1, or I can just write this as 1 minus 1. Okay. So just given some t value, I can easily calculate what this integral is supposed to be, right? Now, once I have this expression, right, in this case, I want to know if there is some way that I can go all the way towards infinity, or if this works as it goes towards infinity, right? So what I'm going to do is I'm going to take this t value, and I'm going to take the limit of this integral as t approaches infinity, right? Because that'll give us what we want. This is the same thing as a statement. When we're talking about this thing, this is what we're thinking about. We're saying, what happens if I let that t value go all the way towards infinity of this integral, right? Let me see what the area looks like in this piece, and let me just see when I expand it all the way. So, again, our process is all the same, right? Doing the integral is still the same, but now we just put the limit onto it. Here, limit here, this. Now, do I know how to find the limit as t approaches infinity of 1 minus 1 over t? Yes, we do. What's going to happen to the 1 over t? It's going to approach 0, and this just approaches 1 because it's 1. So we get 1. So the value of this integral actually exists. So what this says is, if I start from the number 1, and I find the area underneath this curve 1 over x squared from 1 all the way to the right, it actually gets small enough to a point to where I can actually, it's a value. And that value in this case is this 1, right? So it works out nicely. And so again, that's why it's kind of worth to study these sorts of examples, because there are some that will converge for us and will give us some interesting information about the curve. So, any questions thus far on this? Okay, is that because the concept kind of makes sense, introducing it, what we're going for? Okay, good. Now, this integral, right? This work that we've just been doing here with infinity. This is what's called a improper integral. Of okay, and this has to do with all the ones that go towards infinity in some way, shape, or form, right? So if I basically, you have really 3 different cases, right? In this first case, we went to positive infinity, so I have some number and I'm going towards positive infinity. Solve this or to find an answer from it, I'm going to rewrite this as the limit as t approaches infinity of the integral from a to t of x dx. Okay, so that's exactly what we did. This is one case, right? But this is equivalent to this. So if I'm given that integral, I can put a limit outside, evaluate this, and then take the limit afterwards. Okay. Another integral in this category is going to be if I go towards negative infinity, right? So clearly, if I go all the way to the right, hopefully I can go all the way to the left as well, right? And if I taking the integral of x dx, we do the same thing. I would take the limit as t approaches minus infinity of the integral from t to b. Okay, and generally we would hope that the integral here we can do, and then once we're done, we just take a limit corresponding. Okay, and finally we can also, which I won't list it here, but as I mentioned, there are some integrals that go all the way from the right to the left. So as long as both parts of these exist and make sense, then you can kind of put them together to a big one. But yeah, generally we have goes towards infinity or goes towards minus infinity. If you do have, maybe I'll go this anyway. If I do have one that goes towards from minus infinity to infinity of that, then we probably want to approach this by, we can do the limit as t approaches infinity, and then you can do minus t. Again, we should be able to work that one out. Okay, so this is an improper integral type 1, which says that, you know, I'm shooting off towards infinity, and does everything exist that way? Does that make sense? Can I plug in values? Then if so, then these are true statements, and this is going to work. Okay, now let's kind of bring back the discussion real fast to just the thought that I introduced x squared, for example, and was talking about that going towards infinity, but that would not have worked, just clearly seen by the picture, but also even if we try to evaluate the integral of this, right? So infinity of 1 to t of x squared dx. Right, this wouldn't work out. And the reason being, right, so what's the integral of x squared? 1/3 x cubed, thank you. Which, and then we solve our limit. 1 to t, and so we're going to get the limit as t approaches infinity of 1/3 t cubed minus 1/3. Okay, what's going to happen when I plug infinity to that though? Is that going to give me like a number, or what is it? It goes towards infinity, right? It's just infinity, right? So this is just meaningless. I mean, if I just have infinity in general, it's kind of hard to tell what to do with that, right? Because I mean, some infinities are bigger than other ones, right? It's meaningless, right? And so for this reason, whenever we experience an integral like this, we're going to call this one divergent. Okay, so for an integral to be divergent, that just means that either it doesn't exist or it just goes towards infinity, right? Which means that generally in this case it goes towards infinity, which is it's too big, right? Like I guess the space between your curve and the line here is too big for us to say anything, right? But by the contrary, since we found a value for this guy over here, this integral is going to be called convergent. Okay. So basically, if the value exists and is not infinity, then it's convergent. And if the value is infinity or it doesn't exist, then it's divergent. Okay. So you're going to be asked some questions to determine whether it's convergent or divergent. And so that's how you're going to be able to tell them, right? If you solve it, you get something, you get some finite number out of it, then you're good. But if you can't, then that's what we're going to call a divergent one, which is not going to help us for this purpose. Okay. Good. Any other questions so far on that? Okay, good. So let's take a example, right? So this will be, I guess, official example 1 here. And we're going to look at an integral together, and we're going to discuss and see if this is convergent or divergent, right? So we had 1/x², so maybe I'm going to go and I'll still go from 1 to infinity. But we'll do 1/x. So it's a pretty similar situation to what we had. Now the question, so I'm going to say convergent or divergent. Okay, so that's the question. We want to figure out that this is convergent or divergent, and if it's convergent, we want to provide the value for it. Okay, if it's divergent, then it's divergent. Okay, so if I want to solve this integral, right, what's my first step going to be? Yeah, we need to use the limit. We need to rewrite it using the limit, right? Because as of right now, it's a little hard to work with. So I'm going to rewrite this as the limit as t approaches infinity of the integral from 1 to t dx. Okay, good. So now let's just focus on this part. Do I know how to do this integral? Yep, absolutely. What is it going to be? Natural log. So we have the natural log, and it's absolute value technically. It doesn't matter too much since we're in the range of positive numbers anyway, but I digress. Natural log of the absolute value of x, where it's x, and that's going to be from 1 to t. Okay, so I'm going to get the limit as t approaches infinity of the natural log of t minus the natural log of 1. What is the natural log of 1? 0. Good. So that just becomes 0, which is good. Okay. So we're just left with the limit as t approaches infinity of the natural log of t. What is the limit as t approaches infinity of the natural log of t? It's going to be infinity. Yes, the natural log just keeps growing. It just keeps increasing as we move along, right? So what that means is that, so this tends towards infinity, right? The limit goes towards infinity. So is this integral convergent or divergent? It is divergent, okay? Now, again, for some, this might seem like a bit of a surprise as to how that works, but again, I'll just focus on this side. This is 1 over x, and 1 over x squared is, I think, probably considered similar. Lower, okay, and we're talking about this integral here. What happens is that 1 over x, which is the y graph here, compared to y equals 1 over x squared, it decreases, right, or it goes down just a little bit too slowly so that it doesn't ever collapse, like really stop. Like as you keep moving farther, you keep adding things, it still keeps growing. It seems like, you know, that, oh, if 1 over x squared is okay, then 1 over x is going to be fine. But unfortunately, that's not the case. 1 over x is kind of actually is a big threshold in terms of doing these sorts of integrals. There's a problem in the book that talks about it just has x to the p in general, right? So instead of 1 over x, it does 1 over x to the p power. And it asks like for what values of p that this works, right? And funny enough, p works if p is greater than 1, right? So seriously, you could have p be 1.000000, you know, all the way to 0, 1, and you would still be able to get a value out of this integral. It might be a little big, yes, but you would still be able to get a value out of it. But as soon as you hit 1, then everything breaks down, and everything less than that doesn't work. So that's going to be something important to see here, and it's going to be relevant to the future once we get to chapter 11 as well. Okay, how's that so far? Does that make sense? Is that good? Okay, so big idea here is you're doing integrals still, but now you just have to add a limit onto it. And if you get an answer, like a number answer, then it's convergent. But if you can't get a number answer or it's infinity, then it's divergent. Okay, so that's going to be the big gist of all of this.
Okay, makes sense. Okay, cool. Let me go ahead. So that is the limit as we go towards infinity. Now we don't just have type 1 integrals, we also have type 2. So I want to make some space. I'm going to kind of link those out for us of what a type 2 looks like. Because infinity is not the only issue in our case. Okay, so again, to demonstrate this one, let me give you an example. You're gonna take the integral from 0 to of 1 over square root of x Okay. What's wrong with this? Not necessarily the square root, actually. The square root is not a bigger deal. Here. It's undefined as 0, right? So whenever we're thinking about like what the issue is, we want to look at the function. You know, when you integrate it, it might fix something or it might help you, but in this case, when we're checking our values, we don't look at the original function. And as of right now, I can't plug 0 into this, right? And that's an issue, right? Because it's undefined at that point. So, you know, normally I like to be able to have a curve, you know, something like this, so I can just take the 2 points and get the area. But for this question in particular, we're getting something that looks like this, right? So what's happening is I want to evaluate my integral from 0 to 4, right? And everything in here is fine, but then here it doesn't work, like it doesn't exist. Like the value, I'm not touching the curve, really. I can't hit the curve here, right? Because it's undefined at this point. So, but that's all right, because I can still try to work this out. I can see if maybe, just maybe, if I approach it, like if the curve is just right, that I can still say something about what happens to that area, if it converges or not, right? So let's work through this, right? So again, so 0 is the troublesome one, right? So in this case, I'm going to want to rewrite this, right? Just like with the last ones with the limit, okay? Right, because that I want to approach 0, but maybe not actually hit 0, right? Because I can't put 0 in at the moment, but let's see what happens if I take the limit, right? So, and it's okay to use, I'll just use t. What is my limit going to be in this case? What is it? T approaches 0? Almost. We have to be very careful, right? Can I approach 0 from both sides? Why not? Right. So we can't plug in 0 still, right? We know that for sure. And it technically has a definition on when we're approaching it from the left side, but it's not real. Like they're not real numbers, right? Like the square root of -1 or -2, like in this situation don't work. Okay, so those ones are out of the picture, right? So I do not want to just do 0, right? Which maybe for some cases that doesn't matter as much. For here specifically, and in general, we need to acknowledge that we're not just approaching 0 in general, but we're approaching 0 from one side, which is going to be on the positive side, which is going to be the right side in this case. Okay, right? Because my integral, again, I'll draw it. Right? I'm only caring about the integral in here. I don't care about what's happening on this side. I only care about what's happening on this side. So I'm just gonna approach zero from the right side rather than approaching zero from both. Infinity, that didn't matter, right? Because here we're going towards infinity. You don't approach infinity from the right side, right? Because you just, I mean, you can't. So let's go ahead and try to work out this integral now that we've made our limit here, okay? So how am I gonna work this out? What steps do I need to take to integrate this? Okay, yeah, so we're gonna end up using the power rule. Maybe I should try to rewrite this first, right? How should I rewrite that? Side. Fantastic. Okay, so now we can do it. We can use our power rule. So what am I going to get when I use power rule now? Yep, so you can do the word flip around the fractions a little bit, but I'm going to get 2x to the 1/2 from t to 4. So then I'm going to plug in my numbers. So I'm going to get the limit as t approaches 0 from the right side of 2 times 4 to the 1/2 minus 2 times t to the 1/2. Okay, what's 4 to the 1/2? 2. Thank you. Yes. So we get 2 times 2, which is 4, and then minus 2, and I'll just write square root of t here. Okay, so we get this. Now, can I plug in that t approaches 0 from the right now? Yes, we can. What am I going to get when I plug it in? 4. Okay. So that integral is 4. Okay, the number just turns out to be 4. Okay. So again, even though it was undefined at that point, right? It's still converged, right? I could still get something out of it. So this is a convergent integral, right? Unlike our 1 over x example, which was divergent, right? Okay, so let me label this all here. So improper integral of type 2, if we have, right, so actually let's see how they, okay, so we have, if we, let's see, we go from A to B, so let's say for our function that we can plug in A, but we can't plug in B. So B is not included. B is not in the domain. Then the integral from A to B of x dx, rewrite as the limit as t approaches B. Okay, so this one started out. So now we can't include B, right? But I want to approach B. Am I going to approach B from the left side or the right side in this case? We want to approach from the left, right? Because it's the higher number, so we should be reaching up to it. So we're going to approach B from the left side of the integral of from A to T dx. Okay, if we can't plug in A, but I can plug in B, then we're going to take the integral from then A to B of f of x dx is going to be kind of what we just did here. We're going to take the limit as t approaches A from the right side in this case, and we're going to go from t to b dx. Okay, so, and then last one worth mentioning because what if instead of it just being discontinuous on one side, I have a discontinuity in the middle, right? So what I'm saying is, what if I can plug in A and I can plug in B, but there's some C value in between that I can't plug in, right? So what if instead of, like for this problem instead, what if we had right? What if we have 1 over x minus 1 instead, right? Then the problem would be at 0, and the problem would be at 4. It would be at 1, which is in between the two, right? Well, we have this situation. What's going to happen is I can simply just take this, the integral from a to b, that's dx, and I'll rewrite this as the integral from a to c, of x dx, plus the integral from c to b. So I'm going to split it up into 2 integrals, right? And then this one is going to act like this guy. And then this one is going to act like this guy. Okay? So if you have this situation occur where you're discontinuous at some value in between, then you want to split it up into 2, and then you'll do each one in one of these 2 forms. Okay? Which is similar to when I had the type 1 up, going from negative infinity to infinity. You could also say, you could also like choose some value in the middle and then split that up into 2, and then do it like the first case, do it like the second case. But you would hope that in those cases they can easily just plug it in. Okay. Any questions on that? As far?
I have a question.
Yeah,
Is
absolutely.
that a plus sign between the split integral?
Yes.
Or is it plus or minus?
No, it's false. Yep.
So how do you know which side to move?
You just think about the area, right? What you're wanting, right? So if this is the area that I want, right? And this is the discontinuous number right here, right? My area is on the right side of that value. So I'm wanting to approach it from this side, which means I'm approaching it from the positive side, right? From plus, from the right side. But if I was discontinuous here, right? And my area is on the left side, so I should be approaching it from the left side. Okay? And so that'll kind of help you to determine that. Again, you can also just see, like in this case, right? If it exists in my left one but doesn't exist in my right one, then I can take it and I just know it's going to be B from the left or A from the right in that case. That's the idea there. I'm not sure if it, but you wouldn't have that case, but it talks about the case for if you don't have either of them. And I think you can probably just like, you might be able to fix this one between, but again, you won't really have any problems like that. So, okay, good. So let's see. There's one more thing I want to mention here. Again, most of this is pretty intuitive. The work you're doing in the actual integral is stuff that you've already done. There's just the added layer of the limit. So as long as you can take care of like this part generally, then adding this on won't be too hard. And as long as you just know how to rewrite the limit. The last thing I want to mention, so that was essentially 2 cases, and if I have a little bit of time at the end, I can cover that, but I need to make sure to mention all that you needed. We're going to talk about something called comparison theorem. Okay, now this says, so we're going to suppose, right? So we have 2 functions here. It just says suppose. We have a function f of x and g of x, where f of x is greater than or equal to g of x is greater than or equal to 0. Okay, so I have 2 functions, and that's how they're related. They're both always positive. One and f of x is always greater than or equal to g of x at all times. Okay. And this is for some x greater than or equal to a. So you have some defined a value that you're kind of basing everything off of. Okay. We have two parts of this. The first part says if the integral from 0 to infinity, or from a to infinity, apologies, of f of x dx is convergent, then the integral from a to infinity of g of x is okay. Let's think about why this is. Why would this be the case? Why in the world would it be true that if I knew that this one would converge, and that this one would also converge?
X is bigger than.
Exactly. So it all lies in this f of x is greater than g of x here, right? The big issue, right, with when we talk about the 1 over x squared and the 1 over x case, is that 1 over x was too big, right? After that certain point, but 1 over x squared was small enough, right? But and we also, would say that, as I mentioned, 1 over x cubed would also work, 1 over x to the fourth, etc. Right? So what this says, right, 1 over x squared, just for example, 1 over x squared is when we'll say x is greater than or equal to 1 in this case. 1 over x squared is always greater than or less than 1 over x cubed. What do we think? In this range. What do we think? Just plug in some numbers, right? But 2 in there. I'm going to get 1 over 2 squared, which is 1/4. I'm going to get 1 over 2 cubed, which is 1/8, which is bigger, 1/4 or 1/8. 1/4, good. Okay, if I take another number, right? 3, I get 1 over 9, 1 over 27. Which one's bigger? Exactly. And if you kept thinking through that, you would see that 1 over x squared is bigger, right? So, and this is true not only for 1 over x cubed, but basically whenever the number here is bigger than 2, then this is always going to be the case, right? So what this says is if I know that 1 over x squared is convergent, then that means that everything smaller than 1 over x squared is also going to be convergent as well. So 1 over x cubed, it kind of just follows through, right? So this is very useful to say that even if I don't know how to evaluate this function, if I know of a function bigger than that that does converge, then I can safely say that this is going to converge. I may not know what it is, but I know it converges. Okay? Similarly, if the integral from a to infinity of g of x is divergent, then the integral from a to infinity of f of x divergent. Right? So this says that, oh no, g of x is too big for it to converge. Oh, f of x is bigger. That must mean that f of x is also too big to converge, right? Right? If this is too big, right, or if it doesn't go low enough to actually give me a value, then it should be clear that the f itself, if it's bigger at all times, will also not converge, right? It has to follow that way. Does that make sense? Okay, that makes sense. So that's the comparison theorem. Okay, which basically says, right, if I can say, oh, this is right, if I don't know anything about this one, but I do know about this one, it's bigger. And the example they give, which they go from 0 to infinity, I'll just go from 1 to infinity, is e to the like negative x squared dx. So this is not one we can evaluate. This is actually impossible for us to evaluate with any of our methods. Okay, so don't try it; just doesn't work. Okay, but this does have a value, and we can know that for sure because let's think about it, right? I don't know how to integrate e to the negative x squared. But I do know how to integrate e to the negative x power. Right? Now we're talking about 1 to infinity, right? So all I care about is for x greater than or equal to 1. Right? So which one is bigger between these two, do you think? Is it going to be e to the negative x squared, or is it going to be e to the negative x? E to the negative x, right? Because it just, I mean, for example, again, 2, if I get e to the negative 2 versus e to the negative 2 squared, or e to the negative 4, e to the negative 4 is smaller, right? Because it's the exponent's bigger, right? And that's going to be true for all x greater than or equal to 1. And so we have this, right? So if I just look at this integral, instead of doing e to the minus x squared, I do e to the minus x. So let's walk through this together. Let's evaluate this, okay? If I integrate this, how do I start this off? What's my first step? And do the limit, right? We don't just replace it, we gotta make sure we do the limit of the integral from t to 1 to t of e to the negative x dx. What is the integral of e to the negative x? Almost, not just e to the negative x, it's negative e to the negative x. Okay, don't forget about that negative up front, don't forget about u substitution, right? On the formula sheet, it's e to the x is e to the x, right? That's not true in general. We need to be careful, okay? Negative e to the negative x, and make sure that limit's on the front. And we're gonna go from 1 to t, so we get the limit is t approaches infinity of negative e to the negative t minus e to the minus 1. Well, actually, we plus in that case. Okay, this is just e to the minus 1. We can't do anything with that. What's going to happen as I take the limit as t approaches infinity of this thing? It's going to approach 0, right? Because we have e to the negative t power. Go fast. We have right, e to the negative t power looks like this, right? So as I go towards infinity, that thing's definitely shooting towards 0, right? It keeps getting smaller because as your power gets bigger, it's a negative power, so that's going to flip to the denominator, and so the whole number becomes smaller. So I'm going to get 0 here, and then plus e to the negative 1. Yes. Okay. So this integral converges. Okay. Now we just said that this guy is always bigger than or equal to this guy, and it's always positive. They're always positive numbers, right? So what does that tell us about this? Does that mean it converges or it diverges? It converges, right? Because f, which is e to the negative x in this case, which is bigger, since it converges, then g, which is smaller, must also converge. We don't know what the number is, but it exists. Okay? And so that's why that's useful. Okay? Any last questions before we finish up here? Okay. We should have done 2 more samples, but unfortunately not this time. Thank you for listening. We'll start chapter 8 tomorrow, finish chapter 8 on Wednesday, and then we'll start chapter 9 on Thursday, and we'll go from there. No, I'm not worried about it.